This is going to be the last ordinary lecture in this course. So today we will be finished with the necessary theory, and you will be on your own, meaning you have to form groups, start working towards your project. Today, demonstration of a PID controller, and then I'll address a little bit administrative things, some information on the home page. First of all, one administrative question. Some of you have been wondering, how many exercises do I need to be allowed to take the exam? So far, you have been given 6 exercises. You will have number 7 out this week. Should then contain something with a PID controller, of course. And then presumably we are going to make also an exercise number 8. And according to all theory, 2/3 of all the exercises has to be approved. So here, of course, this doesn't really make any sense, does it? What will it be? 16 over 3 doesn't work. Multiplied by 2. Then you have 2 times 16 over 6. The 6 goes. So something like this. Isn't that right? It should be. Let's look here. Never ever show this to your kids. See? Works every time. So 5 exercises should be approved. Okay? We'll do more of the administrative afterwards. Now back to the demonstration. I showed you last time this example with frequency response. So here we had a moving plate and then spring and a mass attached on top. And depending on the frequency we send in, you will have different types of responses. First, you start with a step, this just to determine the natural frequency of the system. And then you can start playing around with different frequencies, maybe far away or close to the natural frequency for your system. So that was last time. And just to repeat, spring and a mass like this. So here we have some y dot or something. And what will the bond graph be? Well, you have here something given as a source, a flow source. So that should now be a 1, where the flow source attacking. Then we have a spring, insert with a 0, and finally another 1. That will be the position for the mass. And he has inertance to it. So that should be the raw bond graph. Of course, you don't need the 1 junctions, so you can skip them. And the simplified bond graph will then be something like this. Very neat, very easy. The flow source, okay, causal stroke has to go like that. Doesn't dictate anything, but you choose, say for the C element, you choose integral causality, then it's given. It has to be like this, hence both energy storage elements on the integral form. It's a second order system. So here then Q dot Q over C, and here P dot P over I. Here we have Y dot, and here we have nothing of interest. Then the common effort is dictated by where we have the stroke, Q over C. So that's one equation for you. And the other one, Q dot, well, and then you use the summation rule around the zero junction. And what comes in equals what goes out. So here we have the given flow source minus P over I. So these are the two equations that we now simulate in this program. What I want to do now is control them. I want to use a PID controller. PID, proportional, integral, differential, or what do you call it? The present, the future, no, the present, the past, and the future. It's also given. And you will then produce a signal. It's a function of time equals, and you should have been taught the following example here. An anode plus 1 over time I integral of the anode dt, and finally here T d multiplied with the derivative of this anode. Present, integral, and differential. Proportional, integral, differential. So I assume you, Alex, taught you that one? Yeah? How to do it here? Well, first time I did it wrong. So what I'm about to do is wrong. But I thought it looked so smart, it looked so clever. So if we try to do it wrong, okay. What I'm about to do here is give this, I want to have a certain behavior on this mass. And the behavior, that's sort of prescribed. Let's see, here we have it down here, yep. So here we go. So now the position, the purple line there, he should go slowly up, stay there, and then go slowly down again, and then finished. And just to give him a challenge, I can change it to a sudden step as well by just removing this one. Now this is the behavior I want. So go linearly up and stay there, and then all of a sudden jump down. So that will be more tricky for him. But that's what I want. And then looking at these equations, then my first maybe obvious choice was then to say the signal here that I want to sort of regulate into my system is this guy, y dot. The anode, well, the anode must now be the difference between the position that I actually want, that I have prescribed, minus the position I actually simulate. What's the position? Well, in the mechanical world, from one graph, that will be Q, the displacement. So there is my anode. And then just program it straightforward. That shouldn't be any big deal, should it? So this is what I did. I have to calculate first, in the beginning of a time step, my new anode. I have the old anode from the previous time step. I have the old position from the previous time step. Now I construct a new position that I want. So this will now be my new anode. Yes?
Can you please draw my closed loop diagram for this?
Well, I don't really like to because it's wrong anyway. If you see my point. No, I don't want to. Make one yourself. So my point is, when you have prescribed the position here, this position for this guy, y wanted. Now the question is, what should the input to my system be? That's the only question. So I started out then with the code, finding a new adduct. For the future, I have to create a derivative of the adduct. So here is just a first order Euler derivative, taking the new adduct minus the old one divided by delta t. So that should now be the future, this one, the derivative. The integral, you just accumulate up all the adducts from all previous time steps. Some people say, well, you don't really have to integrate from 0 here. You could have started, say, from the time t minus a time window, but it really doesn't matter because the adduct is supposed to be small anyway, so you just accumulate zeros, so it really doesn't matter. So here I took everything. So you see the past, I just accumulate up the also a first order approximation of an integral. Then I use this equation directly to construct now my y signal dot here. And having the derivative y dot, well, I also need the position for this plate to have the graphics in order to see how high the altitude is for the mass. So I just again use first order Euler scheme here, finding my new position based on the previous one and now the derivative. So this was my first attempt for a PID regulator. Any questions to the source code? Okay. Then you have 3 parameters you can play around with. The proportional constant actually influencing all 3 terms, and then you have these 2 time constants here that then has to be specified. To make it easy, you have several possibilities here to find a good set of these 3 parameters. And if you just write in Google PID controller, you have the Wikipedia. Wikipedia, very nice place to find information, of course. And all the way down here, you'll find a neat little animation. Here we are, this one. So he says, start with the proportional constant, the KP. Then afterwards, you adjust the time, and finally the integral, and then finally the derivative. And you should do so for the first one to have at least starting to get some oscillations. And when you do that, stronger oscillations, you should half the proportional constants. That should be the first step. The integral term will then be used to adjust the offset if you are not hitting the correct level. Finally, the damping, the differential, he will smooth things down a little bit so you avoid all these stupid oscillations. That's the theory. So now we can start playing around with this in my code. here somewhere. So Kp should now be not 0, but I start with 1. This integral time, remember, is 1 over. So to get, you can't put 0 here. Instead, you put a very big number, 10 to the power 10. And then he is a 0. And then we start. Not a success, no. So we just crash that one. So here I can now play around with different numbers as much as I want. Very small one. Then the arrow is actually quite large and obviously unstable. So I need a bigger one. Or maybe I need some of these others as well, because this, to be honest, is a very nasty problem. I have no damping in the problem whatsoever. So it's very, very unstable, very hard to get correct no matter what you do. So let's add some damping here, say 1, just to see if it helps. Yeah, it seems to be helping a little bit, but no, this is not going well. And so you can continue here. And it really doesn't help either way how you do it. It just gets unstable. So you can play around with this, and it really doesn't help. So here I was getting depressed. So what's wrong? What's the arrow here? Where have I gone wrong? Any suggestions? Not so easy to see. Remember the problem here, the task. Adjust to a specified position. The arrow is defined as difference in position. Then you must not adjust a velocity. You must adjust the position. That was my mistake. I'll show you. So here, what I adjusted here was the velocity directly y dot into my system. But that's not what you have to adjust. You have to adjust actually the position, ys, and here I have to call him nu. Like that. Into my code, I still need the derivative of ys. So here, I now say ys dot equal, and then I make just the first order Euler approximative here, ys nu minus the old one, ys, and then divide by delta t. And then finally here, ys equals the new one, ys nu. Like that. Yeah, I think that's correct. Let's try. Going back here to say he was a very big number, and this one was a, come on, was a very small number. And k was say 1. Now let's see what happens. Behaves a little bit better, don't you think? Still a little violent here, far off what he should have been, but never mind. That was the first one. Now the second one. Let's say he is 1. Why not? See if it helps. Oh, not so much. We need the damping. So let's put him to 1 as well. And now we're talking, now we're talking. To find a good set, of course, you have to play around with these numbers. If I find a good, what did I find? That's the best one. Where are they? 1.1 and 10 was it? 10 and 0.1. You actually see him follows like they were glued together almost. So yes, it is possible, but here another challenge for this program is I can show you here, pause, that I have, it's not a continuous time, and it's just a first order program, so the arrow here is quite large actually, and now he will stop when he hits the first one. So you go from not moving, and all of a sudden you should give him a constant velocity. So that's sort of infinite input. You go from 0 to a sudden value in velocity. So the first, say, position that he calculates is very, very big. So big that it doesn't even enter the screen. And now finally he gets into the screen. So he gives him a really heavy kick, so strong that you don't see it on the screen, and then have to sort of compensate. So the calculation here, it's quite limited what actually he can do, since I have quite a big delta t actually. Nevertheless, he does a fairly decent job, I would say. And even the other, if we go to the step, that's even worse. Where's the step? Should be here. Pause. Okay, here comes the step. So he's really dragging him down. And then he has to compensate, or else he goes too fast. So he can see into the future, remember? That's the derivative. So the position that he obtains is quite good, I would say. Not that much deviation from what I have specified, from position 1 to all of a sudden position 0. You have the blue positions here that are, of course, somewhat off, but still quite decent behavior. So PID controllers, very good news indeed. Any questions to this one? So how to find an optimum set of these coefficients here? Very easy. You know that already, don't you? You have the adduct in your code. You just accumulate sort of the sum of all the adducts for a given time sequence. And then you use that as a cost function for an optimization problem, using f-mean search or f-mean con to find the three desired values for your parameters for an optimum set of these three constants. Of course you do. Which then will be the topic for next exercise. I'll put out these source codes for the vibrating mass, and also this PID. It's not that big a source code actually. Most of it contains of graphics anyway, so I mean this is roughly it. I had to use here a Hoyne method, it's a predictor corrector code, to have a reasonable accuracy. The first order Euler scheme was not accurate enough. But the reason here is that I have to use quite big time steps, or else this is going to take forever. I can show you. Better time resolution here will of course be better, but it's really, really slow. So this is going to take forever. I have to crash him first. Here we go. He's going to stay there. But now he will actually behave much better. But then maybe my choice of parameters was not the optimum anymore, since I have changed the delta t. You changed the entire problem actually. He moves quite decent now. Okay, no questions to that one? That's okay. But then we say enough with the theory for this course. You have been given here the old exams. I'm missing last year's exam, but I will put it out for you. So here you can see what I expect on an ordinary written exam. And you can have a look, but they are quite boring actually. So, but this one you should now recognize, for instance. So it's a very easy exam, very boring. So you have some handwritten solutions for them as well. Some of these old problems, you may risk that the course was a little bit different. Some of them may include thermal problems, which we will skip. So don't panic if you find some material you haven't heard about. If it's thermal, then just forget it. What you also will find here is now something called a poster and project report. So you are to write an article, a report as a project work, and you are to produce one poster. The article has to be on a certain template. Sadly, so far I only found the Word, Microsoft Word template. So you sort of a little bit stuck to Word here. I'll see if I can find other templates, I mean in other editors, LaTeX. But this actually will be realistic when you are thinking of writing a scientific article, sending it into a journal. Each journal will have their own desire, their own format, their own templates. So this is quite standard for actually most journals. Some will accept a manuscript, that's just raw text, and then the figures in the end, and they will sort of organize it for you. But most journals, they will have a template. So use the template, and you will be given page limitations. I would say, what should we say, maximum, how many pages? 8 pages should be enough. That can be hard, so you have to sort of be to the point. You can't just write blah, 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 because 8 pages can be narrow, can be uncomfortably short. But that's sort of part of the job here, to write it straight to the point. For the poster presentation, the entire group will then stand there in front of your poster. Next to the poster you will find, there should be then one copy, one printout of the report. And people going by you will then ask you questions, challenge you, how did you do this, and what is this all about, and so on. And you have to answer nice and politely, because some of these visitors will then be censors. So they will grade you. They will grade the entire group, so you will not obtain individual grades. The entire group gets 1 grade for the poster and the report. That means if you get a question, then the entire group will answer it. Meaning, if you as a person get a question and you have no idea what he's talking about, then you can say, sorry, I didn't work on that part of the project, but my colleague here did. He can answer your question. That's fair. That's okay. So not all of you have to know everything in the project. Okay, you can split it up into different jobs. That's fair. That's fair. Here, the factors for the report. I mean, it's more or less the standard layout for any report, although the sequence is not correct, is it? The first one should then be introduction, where you will describe the planning, scope, definition, maybe also literature study and collection of background data. That's sort of the introduction, isn't it, for any report. Then you have to specify, why is this important? Why have we chosen this problem? And what's the state of the art for this type of problem in the world today? So that's where you start. That's the introduction. For us, we will not do it so strict. Actually, this is supposed to be more fun. So when you invent a totally crazy problem, then you might have problems describing the state of the art today of your crazy little problem. That's okay. So don't stress it too hard. But formally, that's an introduction. Why is this important? State of the art today. Next, you will have theory. Also here, important, as it always is important when you are doing a project, when you're doing the master next year or whatever. Who is your readers? Who are you writing for? Who's going to read this? And here you write it as if the rest of the class is going to read it. Meaning you don't have to describe what is bond graph, for instance. People know that already. So you just use it. For the theory part, you only use as much theory as you need to describe or to explain your crazy results. So theory chapter, that's actually something that you will write almost at the end, when you have to discuss the strange behavior and whatever. Okay, then you need some theory to describe it. Results and discussion. I would normally recommend that you join these two together in one chapter. Results and discussion. For simulation, it will typically be first description of the simulations, different ones if necessary, then the discussion. But I mean, they are so closely linked that you can take the discussion immediately for the different simulations. Much better, or else you will just have to restate all the results and simulations once more in the discussion. Conclusions, of course you need a conclusion. That's an important part. Definitely, that's the only thing that the journalist reads afterwards. So that's important. And there, of course, you can, if you want, hook up some ideas for further work if somebody else is going to continue. For the poster, not that many points. So the poster does not actually have to be a complete report layout. But some things definitely has to be present. You will be given a group number. So group and name, yes, they have to be on top. And then some principal sketches, of course, what's this all about. But then not all of the results. You don't have space. When you print out a poster, it should be readable. If the poster is lying on the ground, you should be able to read everything. That's the demand. So no tiny small little letters here. Use a little bit bigger font so that it's possible to read it. Also, with the poster you can have a little bit more fun. I mean, that's more the PR. You can sort of capture the audience a little bit, produce or show them some of the fancy results. You can maybe even show some results that is not in the report. I mean, the report is there anyway. So the report, that's the more scientific part of it. The poster can be a little bit more PR, just to catch the audience a little bit. So there you can have a little bit more fun. I think even you find some poster tips here. Yeah. Here you have it. So what, at least in my opinion, should be present in a poster. But as I say, it's only guidelines. So it will depend on your choice of problem, of course it will. And of course everything in English, also the report, everything in English. I think I said this before, don't make one big expensive poster. It costs a lot, 1,000 crowns at least, to have it printed as an A0 poster. So what you do, you specify a sheet of this size, and then you construct your poster in Word, PowerPoint, whatever. Print it out as a PDF file, and then you bring it to me. Then I can help you print it out on a color printer with A3 sheets. It will then be some hours with scissors and glue to patch it all together to one big piece of paper, but it will be quite nice. If you like, you don't have to do it like that. You can have your poster consisting of separate sheets, A3 or A4 for that matter. And then of course you won't have one sentence across the several sheets. Then you have to sort of split it up into individual blocks, but that's quite okay. One advantage here is of course that when the night before presentation you find a terrible bug in your code and you have to re-simulate some of the results. Of course you find the bug in the end, everybody does that. Then this one is totally wrong. But now you only need to print one page. If you had made one entire poster, then you have to print the entire thing. So that's something to think about. Also then it takes some time to print it out, so a day or two before the presentation the poster should be finished. Also the report, I want a draft report a couple of days in advance, so I can send it to my censors so they can prepare some nasty questions for you. So for the rest of the semester you will then be working in groups towards your presentation. So I will be now present the next lecture here. If you have ideas, ask me, come talk to me, and then I can help you sort of designing your own project. And to be honest, it can actually be any problem. No strong guidelines there. As long as it's a dynamic system that ends up in a set of ordinary differential equations, then I'm happy. But even that, if you are into partial differential equations, we might even find something there as well. So anything will go. If you're interested in traffic control, for instance, I have some ideas. I don't think I brought that program with me. No, Or if you need help with the graphics, because that's always nice for a poster presentation, to have a laptop standing there, doing some simulations, have some nice animation, is very eye-catching. So come talk to me, I can help you with the graphics. That's not something that you should spend time on unless you are totally nerds like me. Then come ask me, I can easily help you with the graphics, no problem. So 1 hour today. Tomorrow then I would suggest you sort of organize yourself into groups, start brainstorming, what should we do? And I will run around asking questions, answering questions, maybe help you to get some ideas. But that will then be tomorrow. So any questions? No? Nothing that we should take together? We still haven't decided the date for the presentation. That's something that will come up. So the information will then be on the homepage. We will have some suggestions, and then you may say yes or no, or I don't like the suggestion, or something like that. More of that later. Okay, but then we stop here. I will be present the next hour, so if you have any questions, ask me.